Greetings, everybody. In my talk today, I propose a new paradigm for fracture healing, one that is based on gradients. We stumbled on this while doing some research on scaphoid fractures. When we compared the optical densities across fracture lines in scaphoids, we found that those showing a greater difference in optical density, or to use a more technical term, a higher optical density gradient, were more likely to result in non-union. As these gradients are induced by the fractures, we refer to them as fracture-induced gradients or simply as FIGs. To further study the phenomenon of FIGs, systematically, we analyzed a series of digital X-rays. On each of them, we measured and normalized the averaged optical density in 7 areas. When we plotted these 7 values, we found some interesting results. First, that from the proximal to the distal end, normal scaphoids show a slight natural gradient of about -10%. Second, that fractures show up on X-rays as acutely formed gradients, and that if we follow the optical densities in fractured scaphoids, over time they fluctuate with gradients that initially rise and later fall to their normal natural gradient. And finally, and possibly most interestingly, we noticed the gradient between the proximal and the distal ends of the scaphoid was very different between fractures headed for union and non-union. And importantly, these differences appeared as early as the first week after the fracture. We soon realized that these observations also had some very powerful clinical applications. I will only discuss 2 of them today. The first one is to predict non-union. So if we use -30% as the cutoff to distinguish between fractures headed for union and non-union, then this test would have a sensitivity of 92% in detecting scaphoid non-union. I will illustrate this technique with a case report. Mr. P was a young man who sustained a wrist injury. 11 days later, he had an X-ray in which the radiologist reported a minimally displaced transverse fracture. 39 days later, his X-ray was reported as indicating union. 53 days after the injury, it showed good healing. And 88 days later, all appeared well to the radiologist. However, because of ongoing pain, a CT scan done on day 88 showed non-union, which was confirmed again a month later with another CT scan. He went on to have surgery 2 weeks later, that is a full 19 weeks after the initial injury. But if we look at the FIGs between the proximal and distal end, they're quite high from the outset, around 30% or higher. It is possible that using the FIGs technique, we could have diagnosed a high probability of non-union from the very first X-ray and surgically intervene much earlier, saving the patient a great deal of inconvenience. Let me now describe a second tool. Consider how we immobilize fractures, irrespective of whether it is my 78-year-old mother, myself, or my 26-year-old daughter. If any of us broke a forearm bone, we would all have it in a cast for 6 weeks. Why 6 weeks? It's quite unlikely that my daughter should need nearly as long as me to heal a fracture, or that I should need as long as my mother. Yet we choose 6 weeks because it functions as the safest common denominator. If we had a biomarker which could tell us when fractures have healed, we could individualize the period of immobilization. The transient gradients we discovered provide such a biomarker. I'd like to state that measuring fracture-induced gradients has the potential to transform clinical orthopedics. So far, I have discussed the clinical application of FIGs. But it is the scientific import of this idea that is probably even more exciting. Devoid of the blood and drama, a fracture is simply a bony gradient. And fracture healing is simply the resolution of that gradient. But there are some key differences. The gradient that results from a fracture is one that is acutely created, and being in a bone, it is a fixed gradient. By contrast, the resolution of this gradient resulting in fracture healing is a gradual process, one that is facilitated by the chemotactic migration of osteoblasts and other cells. A bit of copy editing will then yield a definition that fracture healing is the gradual chemotactic resolution of an acutely created fixed bony gradient. Is this a significant definition, or is it simply stating the obvious? Besides the clinical tools I described and potentially billions of dollars in economic value, positing fractures as gradients provides a whole new way to think about fractures. It moves us from structure to function, from anatomy to physiology, from the static to the dynamic. In that sense, one may go so far as to say, this is not simply a new definition for fracture healing, but one that changes the scientific paradigm within which we have operated for the last few centuries. To me, this has been the most exciting part of the work. Let me now change gears slightly. While I'm very pleased to be presenting this on the International Women's Day, I'm also acutely aware of why such a day is necessary. Though globally we are seeing women tending to parity with men in graduating from medical schools, by the time orthopedic training is completed, more than 96% are men. Numerically, women have been and remain marginal in orthopedics. It has long been asserted by the male practitioners of orthopedics that this is not a specialty suited to the fairest sex because of the need for brute force. Picture this: a few men holding down a screaming victim of a saber-toothed tiger's attack, having bottles of benumbing hemlock poured down his throat while having his leg amputated with a large saw. In such a situation, I would gladly defer to a male surgeon. Yet this image belongs on the walls of old royal colleges. Times have changed, societal values have changed, and importantly, technology has changed. Developments in anesthetics, muscle relaxants, and power instruments have leveled the playing field with respect to the need for strength. The focus today is on good technique, and brute strength may even be a disadvantage. However, the attitude to women in orthopedics has not changed apace. This has seriously affected the scientific development of orthopedics. Fracture treatment as we practice it today grew out of the bone setter's trade. In principle, what we do is really no different from what our medieval counterparts did. We immobilize fractures and wait for nature to provide healing. Though the results we produce today are better, this is mainly because of developments in areas outside orthopedics, areas like anesthesia, antisepsis, and material sciences. However, from within, orthopedics has produced very little scientifically. Our approaches have largely remained ossified within the mindset of medieval bone setters. Various academic disciplines globally have shown us that their own paths to greater scientific development have been paved through the modernization of their workforce by the inclusion of women. Orthopedics has spectacularly failed in this regard, and we need to learn from them, not because women need orthopedics, but because orthopedics needs women for its own scientific advancement. When I see what Indian lady orthopedic surgeons are achieving, and with good leadership, it provides reason for optimism that the future of orthopedics will be much brighter than its past. It's not surprising that this is happening in the country which has twice as many women pilots as the global average. I would like to congratulate you all for your stewardship and leadership in modernizing orthopedics. Thank you.